So let's go over Chapter 8 Practice Part 1. Problem 1, we need to convert 259.3 kilocalories to joule. Let's take a look at the handout and see what are the relationships that are given to us. We know that per the handout that I gave you, we know that 1 calorie is equal to, and I don't have room here, so let me do it here. We know from the handout that I gave you that 1 calorie is 4.184 joule, and we know that a kilocalorie is equal to 1,000 calories. So here, our plan is to convert from kilocalorie that is given to joule that is desired. Okay? We don't have the direct relationship between kilocalorie and joule, but we have here a common unit that is the calorie. Therefore, our plan will be to go from kilocalorie using the second relationship to convert from kilocalorie to calorie, and finally convert from calories to joule. If we did this, we went from the given unit kilocalorie to the desired unit joule, going through the base unit here, calorie. Okay, the common unit that is a calorie. Let's plug in the data. We're given 259.3 kilocalorie here. Per the relationship given in the handout, 1 kilocalorie is 1,000 calorie. Anyway, you knew that K was 10 to the third from chapter 2. And then we know that a calorie is 4.184 joule. These two conversion factors here are both exact. Okay, the first one is the use of prefixes, same system, so it's exact. And the second one is the definition of the calories, so it's exact as well. Therefore, you will plug this into your calculator and you will get to 4 sig figs, because we start here with 4 sig figs. So your answer should be given to 4 sig figs as 1.085 times 10 to the 6th, and don't forget your unit joule. Problem number 2. You have to write a balanced chemical equation for each of the following reactions. We have to include the heat with the reactants or product as appropriate. Our first reaction consists of a physical change between from a carbon dioxide solid to carbon dioxide gas. We are informed that this change is endothermic. So what means that the change is endothermic? It means that the heat goes in. What is our equation? We want to go from solid to gas, and we're talking about carbon dioxide, therefore we're talking about CO2. Let's write the equation. CO2 solid turn into CO2 gas. This is actually called sublimation. Since the heat has to go in, the heat will be in the reactant side. The heat has to be added to the system. And therefore, we're going to add the heat on the reactant side to the system. This is a gain of energy by the system. So the Q, energy heat, will be positive. The second reaction, potassium solid reacts with chlorine gas to form potassium chloride. Potassium solid is K for potassium solid. Chlorine gas, remember your diatomic element, Cl2 gas to form solid potassium chloride, KCl solid, K plus Cl minus combine in a 1-to-1 ratio to give KCl. They react, they form. Don't forget that we need to balance the chemical equation. We have 2 chlorine here, so we're going to need to place a 2 here to have 2 chlorine. And by placing a 2 here, we need a 2 here to have 2 potassium on the left side. We're told that this change is exothermic. So what means that the change is exothermic? The heat gets out. Okay, it's going to be on the product side. So when I'm going to write the equation, I'm going to let the heat go being lost by the system. Again, the heat is lost by the system. Therefore, it's a loss of energy by the system, and Q will be negative. Now that we have a better idea of the concepts, okay, and how to include the heat in equation where the process is endothermic or exothermic, let's apply number to that. So how do we connect heat energy and temperature? Problem number 3. Gold has a specific heat of 0.39 joule per gram degree Celsius. What is the specific heat? It means that if I want to raise the temperature of 1 gram of gold 1 degree Celsius, I need to apply 0.39 joules. Okay, so here, this is what we call the specific heat, and the symbol for specific heat is small s. The question is asking how many calorie of heat. So we're looking for heat. The symbol of heat is Q, and we want this answer into calories. Are required to raise the temperature of 100 gram of a gold bar. So this is the mass, the weight, the mass in gram of the gold bar, symbol M, and we want to raise this temperature by, so that's the change in temperature. Raise the temperature means that here we have what is called the delta T, the change in temperature. And the change is positive because we want to raise the temperature. The change, it's actually equal to final minus initial. Therefore, is final temperature is greater than the initial, the delta T is positive. Otherwise, if the final is less than the initial, your delta T will be negative, and it will be decrease in temperature for our system. The relationship we're going to be using is called Q equal M S delta T, or Q is the heat, M is the mass, S is the specific heat, and delta T is the change. Okay, so again we have the heat, the mass, the specific heat, and the change in temperature. So let's take a look at this and apply the different values. We have 100.0 gram of gold bar. The gold has a specific heat of 0.39 joule per gram degree Celsius, and our delta T is 15.0 degrees Celsius. Notice that the unit cancel properly, the gram with the gram, and the Celsius with the Celsius. So we're left with joule, which is a unit of energy. Therefore, we get Q equal to 585 joules. This answer is given to us to 4, 2, 3, so therefore two sig figs. It's since we have 4 sig figs here, 2 sig figs here, the leading zero don't count, and 3 sig figs here, we go with the least amount of sig figs. But be careful, the question asks for, again, calories. Therefore, we need to perform the conversion from joule to calorie. We know that we have to cancel the joule and convert to calorie. Per definition, 1 calorie is 1.84 joule. Therefore, your answer to 2 sig figs is 140 calories, small calories, or 1.4 times 10 to the second calorie. Again, 2 sig figs. Let's take a look at problem number 4 now. An engineer tests the thermal properties of a metal alloy. So you know that an alloy is an homogeneous mixture. We have seen in the beginning of the semester. Using a 50.0 gram sample, so this is our mass here in gram, she finds that adding 485 joule of heat energy, we're adding the energy to the system, so Q is positive. And how much are we adding? We're adding 485 joules, okay? So this is Q here. And the temperature changes, so here is our temperature change, so that's our delta T. And we're looking this time for the specific heat of this alloy. So we're looking for S. We know, again, that Q equal MS delta T. And we're looking for S. So we need to solve for S. So how do we solve for S? We're going to, first of all, divide on each side by M. Therefore, our mass cancel here. And then we're going to divide on each side by delta T. And therefore, we get a new equation here. That is that S, the specific heat, is equal to Q over M delta T, which is the same thing as Q over delta Tm, okay? So let's plug in the data now. Q is equal to 485 joules. Our mass of the sample is 50.0 gram, and our delta T is 4.10 degrees Celsius. Notice that none of the unit cancel, and we're left with joule per gram Celsius, which are the units of the specific heat, joule per gram Celsius. So we can check that we correctly set up our equation. We're going to plug this into the calculator, and we get S to 3 sig figs, that is equal to 2.37 joule per gram degree Celsius. So that is the specific heat of our alloy. And again, what do we have? 3 sig figs. 3, 3, 3. My answer is given to 3 sig figs, and don't forget your unit. Problem number 5. Tin has a specific heat of 0.21 joule per gram degree Celsius. We have a sheet of tin that has a mass of 3.2 kilogram that absorbs, so gain this much energy. So again, here is the specific heat for tin. This is the mass for tin, and this is the Q is positive because it's absorbed, and our Q is plus 8.4 kilojoules. And we want to know how much will the temperature increase. So we're told already that this is an increase, so we can expect delta T to be positive. And we're looking for delta T. It's or no. So we're going to go back to our same equation, right? Q equal ms delta T. But this time we're going to be solving for delta T. Therefore, divide on each side by m again, so m cancels, and then divide by s, so s cancel, and you get your new equation as being delta T equal Q over ms. So we're going to plug in the data. Equal Q 8.4 kilojoules over M 3.2 kilogram times S 0.21 joule per gram degree Celsius. And you guys remember when we were taking a look at the unit and verifying what was to cancel, and I told you it's very important? Well, here it is. We have kilogram and gram, so they won't cancel. And then we have kilojoule and joule, so we have unit problem, and we need to convert our energy to joules. And we know that 1 kilojoule is 1,000 joule, and we need to convert as well our kilograms to grams, and we know that 1 kilogram is 1,000 grams. So therefore, let's do it. Delta T is equal to 8.4 times 10 to the third joule over 3.2 times 10 to the third gram times 0.21 joule per gram Celsius. Our joule cancel now, our gram cancel, and we're left with 1 over 1 over C, so the delta C come back up, and we get our delta T to 2 sig figs as 13 degrees Celsius. So the increase of temperature will be of 13 degrees Celsius. Just wanted to remind you that what I did is 8.4 kilojoules time, cancel the kilojoule, convert to joule. 1 kilojoule is 1,000 joule equal 8.4 10 to the third joule, and that for the mass 3.2 kilogram time, cancel the kilogram, convert to gram. 1 kilogram is 1,000 gram equal 3.2 times 10 to the third gram. Okay, just in case you were wondering how I did this conversion here and that conversion here. Let's go to the back of the page now. Problem 6. An insulated vessel, a reaction vessel, has a heat capacity of 105.32 kilojoule per degree Celsius. So here, notice that we're not talking about specific heat capacity. We're talking simply about heat capacity. And therefore, we have a difference in unit. The unit is now kilojoule per degree Celsius. This is not mass dependent anymore. We are given an initial temperature. So here is our initial temperature. I forgot to give you the symbol. For heat capacity, it's just C. And we're told that 1.00010 to the third kilojoule of heat energy is added to the system. Again, the heat is added, so Q is positive, and this is Q. We want to know what temperature will the reaction vessel reach. So we're looking for the temperature reach, therefore we're looking for the final temp. This is our no. This is a two-step problem, okay? So, why? First of all, we know that when we talk about heat capacity, which is independent from mass, the relationship is Q equal C delta T. Okay? What is delta T? Delta T is the change in temp. So delta T is equal to TF minus TI. We know TI and we're looking for TF. Okay? Instead of directly solving for TF, what are we going to do? Because we don't know TF, we don't know delta T. So our first unknown will be actually delta T. Okay? Delta T is our first unknown. Once we have delta T, it's going to make it easier for us to find TF. So let's find delta T first. We're going to divide by C on both sides. So we get delta T equal Q over C equal 1.000 times 10 to the third. Kilojoule over C, 105.32 kilojoule per degree Celsius. Our unit cancel. We plug this into our calculator and we get a delta T in Celsius of 9.495 degrees Celsius. Let's take a look at sig figs. We have 4 here, 5 here, so our answer is given to 4 sig figs. Again, 4 sig figs here, 5 sig figs here. Answer to least amount of sig fig, 4 sig figs. Now that we have delta T, we can solve for TF. Why? We know that delta T is equal to TF minus TI. Therefore, we're going to add TI on both sides and we get TF equal delta T plus TI equal 9.495 degrees Celsius plus TI 24.3 degrees Celsius. Here, be super careful. It's an addition, so we're going by decimal places. 3 decimal places, 1 decimal place. Your answer will be given to 1 decimal place as TF equal 33.8 degrees Celsius. And this is the final temp that the reaction vessel will reach. Take a look at problem 7 now. These problems are not more complex, but it's very important to understand and illustrate the problem to understand how this works. A chemist conducts a calorimetry experiment on an unknown metal. The mass of the sample is 52.4 grams. The chemist heats the metal to 100 degrees Celsius, then place it in a coffee cup calorimeter containing 95.4 grams of water. The temp of the water rises from 21.9 to 23.2 degrees Celsius. There's a lot of information here, okay? So it's very important to understand what problem 7 is by using a diagram. I'm giving you the diagram here, but it will be your job during exam or homework to draw your own diagram. So we're talking about what is called a calorimetry experiment, and we have an unknown metal, okay? So here is our unknown metal. The mass, okay, of our unknown metal is 52.4 grams. So this here, unknown metal, the mass is 52.4 grams. The chemist heats the metal to 100 Celsius. So the initial temperature of this piece of metal is 100.0 degrees Celsius. Then what happened? The chemist place the metal in a coffee cup calorimeter. So the chemist will grab this guy and place it in there. Okay? this coffee cup calorimeter contains 95.4 grams of water. So here, what I have is water. Okay? So this information were about the unknown metal. And here now, I'm talking about water. And I have 95.4 grams of water. That's initial. This water is initially rises from 2. So this is the initial temperature of water, and this is the final temp of water. So initially, this water reads 21.9 degrees Celsius. Then again, the chemist placed the metal in the coffee cup calorimeter. And what happened? Now that our metal that is at 100 degrees Celsius initially, I remind you, goes in the water. Okay, there we observe a transfer of energy from the metal that is very hot to the water. The metal actually here loses the energy, and this energy that is lost, the energy is gained by the water. Remember that energy cannot be created or destroyed, therefore energy can only be transferred. What is lost by the metal is gained by the water. And because the energy is gained by the water, guess what happened when we read the thermometer once we reach equilibrium, which means like hold the metal and the water have the same temp, then the final temp is equal to 23.2 degrees Celsius. Very important to understand that this temperature here is the final temperature for both metal and water, because the system reached what is called equilibrium. Okay, so now that we understand better what the problem is talking about, let's complete the table. The change is the change in temperature, okay, and this change is equal to, you guys remember delta T is final minus initial. So for the metal, the change is 23.2 Celsius minus the initial 100.0 Celsius. So therefore our change for the metal is negative, since we're losing the heat, 76.8 degrees Celsius. This heat that is lost, okay, this by the metal is gained by the water. Therefore the delta T will increase for the water from the final being 23.2 Celsius from minus the initial 21.9 Celsius. So we have an increase here of 1.3 degrees Celsius. So what's the result? The result is that the metal cools down and the water surrounding the metal warms up, because the heat is released by the metal, transferred to the water that gains this heat. Since the heat is released by the metal, okay, the heat is lost. It's lost. It's a heat loss. So Q is negative. And then the heat, it's a heat gain for the water. So the Q of the water will be positive, and here again I have a transfer of energy. So this is Q metal, and this is Q water. This is delta T for the water, and this one here is delta T for the metal. The first question, okay, ask about the heat change for the water. So we're looking for QW. QW is equal to MW times SW times delta TW. Here is your delta TW. Here is your MW. And here is your SW. We have 95.4 grams of water, a specific heat of 4.184 joule per gram degree Celsius, and the delta T that we just calculated up there, 1.3 degrees Celsius. So this is QW. Therefore, QW is equal to 2 sig figs to 520 joules. 3, 4, exact. 4 and 2. Answer to 2. Okay, so this is 3 sig fig for the mass, 4 sig fig for the specific heat, 2 sig figs here, so 2 sig figs is your answer. You can also write this as 5.2 times 10 to the second joule. It's up to you. Now we're looking for the heat change for the metal. Well, remember that we said that the energy is transferred. The energy is transferred from the metal to the water. Okay, therefore, since energy can never be energy, cannot be created or destroyed, what is lost by the metal is gained by the water. So Q water plus Q metal equal 0. Therefore, Q water equal minus Q metal. So it's very easy to find the Q of the metal. It's equal to the opposite of the water. It's minus 520 joule, or minus 5.2 times 10 to the second joule. And again, the reason is because here, what energy cannot be created or destroyed. So what is lost by one is gained by the other system. Now, we need to find the specific heat of the metal. So for this one, we'll be using the equation Q metal equal M metal S metal delta T metal. We have the delta T of the metal already. We're looking for this one, it's our unknown. We have the mass of the metal, it's here, and we know the Q of the metal, it's right there. And we could use another color. We have the Q of the metal, it's right there. Therefore, we need to divide on each side by delta M to isolate SM, and then we're going to divide on each side by the mass of the metal. and we get our new equation that specific heat of metal is equal to Q of the metal over mass of the metal times delta T of the metal. So S metal is equal to minus 520 joule over 52.4 gram times minus 76.8 Celsius. Look at the unit, joule per gram Celsius. This gives you a specific heat for the metal to 2 sig figs of 0.30 joule per gram Celsius.